Last week, we started seeing an overview of the TCP IP architecture. We will continue that today, and we will also continue with the details of the network layer itself, so the center of the architecture. A few words about the physical layer. The physical layer is the mechanisms by which information is actually transported. We will say very few words about it. There are several courses in different sections of EPFL that will talk about it, but we need to know a few things. I mean, first, a mental model of what the physical layer is doing. So the physical layer is taking strings of bits, perhaps individual bits for old physical layers, blocks of bits that are called symbols by more recent physical layers, and then the job is to translate that into physical carrier that can transport the information. With very few exceptions, that's always an electromagnetic wave. As you know, all electromagnetic waves are of the same nature, but they differ in how we perceive them. You have optical fibers that contain electromagnetic waves that is visible light, and you have radio waves that are used with Wi-Fi or cable transmission systems like on Ethernet. Sometimes, unfortunately for the whales and the under-ocean life, we can also use acoustic waves, so you can transport bits using sound instead of light. This is typically done underwater because the electromagnetic waves don't go through heavy, don't go through water very well, so they stay only at the surface. And this is what is used for communication between submarines, for example. What is visible for us of the physical layer is a few parameters. One of them is the bit rate. The bit rate is how many bits per second a given physical layer is able to carry. It's very often called the bandwidth in computer science literature. But if you are interested in physical layer technology, this is not the bandwidth. The bandwidth is in the spectral domain. It is in the world of frequencies. And for old systems, there was a one-to-one mapping of bits per second and hertz of bit rate and frequency. But for more modern systems, it is not the case. But you will find this terminology in the literature. Here are the range of bit rate that we see today. Most modern equipment are in the megabits per second range, but you find older equipment or more resource-limited equipment that has much lower bit rates. For example, if you're using a satellite phone because you're reporting on the war in the Middle East, and that's the only mechanism you have, you will probably have a few kilobits per second. On the other end of the spectrum, if you're doing massive computing inside a computer room, you will have several tens of gigabits per second between computers. And one of the peculiarities of the TCP IP architecture is that it's supposed to work across all those ranges of parameters, which is quite unique. If you design a vehicle to carry you at a few kilometers per hour, you probably design a bicycle. If you design a vehicle to carry you at 1,000 kilometers per hour, you probably design a jet, an airplane, which are very different things. Here, the same protocols, the same set of tools has to work across all this range, and it does work, and we will see what are the implications. So here's our first quiz to make sure you understand the basic math that's behind that. I have to transmit 1 megabyte, and I'm very unfortunate, I have only 10 kilobits per second, which is what you have, for example, when you're in a place of Switzerland where there is only Swisscom Edge access. There are places like this when you go hiking in the mountains, and you want to download one photo, 1 megabyte. How much time will it take? Closing. So you should see on your computer that the majority is voting for A, which is the correct answer. Of course, the transmission time is the number of bits divided by the speed. If you're in doubt, just think of the units. Bits divided by bits per second gives seconds. Now, a byte is 8 bits, so you have a factor rate. This is why many of you said 100 seconds, but that's 800 seconds, which is a quarter of an hour. That's the time it takes to transfer one image over edge, so don't do it. Probably it will kill your battery. So that's one first parameter that we see that time has an impact, and of course we want higher bit rates to have smaller transfer time. There's another parameter that's often confused with the bit rate. For example, if you walk around in the city, you will see cars that are saying they are laying optical fiber, therefore they're giving you the ability to surf at the speed of light, which is true, but is also true for all the other technologies, because light and other electromagnetic waves have, roughly speaking, the same speed. So even Swisscom Edge at 10 kilobit per second is propagating at the speed of light, but the bit rate is not very large. So what is the speed of light? What does it have to do here? Well, the speed of light is the time it takes for the beginning of a signal to move around in space. As you know, light is not instantaneous. It takes some time to propagate. So when I'm sending a signal from A to B, I need a number of periods of my modulation that are shown by square modulation here on this graph, which is probably a very primitive system. That's what we have on 10 megabit per second Ethernet, for example. And how fast the modulation happens is the bit rate, how many symbols per second. But regardless of that, there is a propagation delay, which is the time it takes for the front of the wave to go from source to destination, right? So the propagation delay is given by the speed of light or the speed of the electromagnetic wave that depends only on the medium that we're going through. The speed is the same regardless of the frequency, but the medium is may make a difference. In a vacuum or in the air, it's 300,000 kilometers per second. So it's 3 × 10⁸. In other medium, like glass or copper, it's a bit less, but not much. So roughly speaking, the same. So for example, I'll skip one of the questions here. What is the propagation time it takes to go around the Earth? Around the Earth is what you did in the lab 1 when you did a ping to New Zealand, for example. You send a very short message to New Zealand and back. New Zealand is almost exactly at the antipode of us. So when the signal goes there and back, it makes practically a round trip of the Earth. So how much time is the pure propagation? And the majority gives the correct answer, which is C, 200 milliseconds. Again, it's a straightforward computation. Here I assume the propagation time is 2 × 10⁸, which is plus or minus 10% the true value. So this is why we find 200 milliseconds. So is 200 milliseconds much? Well, yes and no. Here are a comparison of the transmission versus propagation time for different scenarios. On the left, you go not so far over Swisscom Edge, for example. And what is the time to send 1 kilobyte? So what is just an SMS, a texto. Then the transmission time is 800 milliseconds. The propagation time is 0.1. So the transmission time is very large. The propagation time is negligible, which is what we feel in common perception. The speed of light is invisible to us. So we see that in this scenario. But if we go to another scenario, which is sending 1 kilobyte, so 1 short text to New Zealand, and assume we have 1 megabit per second. So 1 megabit per second is doable today to New Zealand if you have high-speed access to the internet here, if you have a good internet service provider, and the same at the destination, then you can easily get 1 megabit per second. In this case, the propagation time is 100 milliseconds and the transmission is 8. In other words, when I'm sending one packet, 1 kilobyte is probably one packet, it takes much, much more time for the propagation than the actual transmission. So we have those two extremes here. And as we will see in a minute, this shows up in the design of some of the protocols. Before discussing this, I need to introduce a third term called the throughput. We have the bit rate, the propagation time, and the throughput. The throughput is like the bit rate, but is the useful part of the bit rate that is for you, for the job you're doing. When I'm transferring some data over a system, the throughput is how many bits per second I can transfer. So if I have a long file to transmit, I count the time it takes to transmit it, and the number of bits divided by the time gives me the throughput. Of course, by doing that, I'm ignoring the propagation time, but I can do it if the file is very long. It's not the same as the bit rate for various reasons. First, an obvious reason is I'm not alone on the internet. If I'm transferring data to New Zealand, then perhaps there are hundreds of thousands of people like me, so I'm sharing the channel with others. And of course, how much I will get depends on how sharing is done in the internet. That will be the topic of the congestion control chapter that we will see a bit later. Now, assuming I'm alone to transmit to New Zealand, even then, the throughput I will get will not be equal to the bit rate, to the practical capacity of the transmission medium, for two reasons. I mean, one is obvious, that's the protocol overhead. We have seen that in order to transmit some information, we put things like IP addresses, perhaps even MAC addresses. We will see that the IP header contains, in fact, a lot of information. The IPv6 header is 40 bytes. So if I transmit 1 bit, I still have to transmit 40 bytes. And there are other headers, TCP, UDP. So we transmit a bit less because of that. That's obvious. The other one is because of the efficiency of the protocol. And I'll quickly go through this. Here is a simple example of how the efficiency could hit us. Here I'm showing a simple protocol, if you want a transport layer protocol, that is trying to repair losses by detecting that whether a packet is correctly transmitted or not. So I have A sending a packet to B, and when B receives the packet, it's supposed to send an acknowledgement, which is the green line. So it sends a short packet in the reverse direction. When A receives the green packet, A is happy, has received, it knows that B has received the stuff, and it continues sending. This protocol is called sometimes the stop and go, stop and wait. It is stop and go in the sense that A sends, then stops sending, waits for the acknowledgement, and sends again. This is what you have to implement if you use UDP. This or a more sophisticated version of that. If you send information using UDP, UDP, remember, does not take care of detecting losses and repairing them. So you send data over the internet, for example, a DNS query. What is the IP address of this server? This is sent over UDP. You send a request, very likely it will be received, but it's not exactly sure. So if the packet is lost, what does your software do? Does it wait forever and hang? No, it will see if nothing comes back. If nothing comes back, it will send again. So that's an example where the application layer has to implement some protocol for reliability. Here is a simple one. Now, if we analyze what is the throughput of this protocol, meaning how many red bits we can transmit over a period of time, rescaled in per unit. Then we can simply say, well, I look at the horizontal axis, and over a long period of time, when they will see that we will repeat the same cycle again and again, if there is no loss. So here I'm computing the throughput if there is no loss. Then we will see that the throughput is equal to capital L, the number of bits that is in a packet, divided by the time it takes to complete an entire cycle. And the cycle is made of the transmission time, T, the propagation time from A to B, the transmission time of the acknowledgement, which is T prime, and the propagation time from B to A, which is assumed here to be symmetrical, which is not always true, which is D again. So this is why we have 2D. So the time it takes to complete one cycle of transmission of one block of information is T plus T prime plus 2D. So the formula for the throughput would be given by this one here. If I compute this for the specific example we've seen before, here are the efficiencies we would get. The efficiency is the throughput divided by the bit rate. In the first case, where I had a very short propagation time compared to the transmission time, both are bad, but the transmission time is dominant. Or in the last 3 and 4 cases where things are good, but the propagation time is small, then we find that we lose very little because the time wasted in waiting for the acknowledgement plus the time spent in propagation is very small. So we are close to 99, 97, 98%. In the second case, when I'm transmitting to New Zealand, I have 3.8%, which means this protocol doesn't work. It works if you have one message to send, but if you have 1,000 messages to send, it will take you 30 times more time than you would need if you had a smarter protocol. A smarter protocol is called TCP. So when we will study the transport layer, we will see how TCP can get rid of this problem. Because remember, TCP, like all the internet protocols, were invented with the job goal of being able to scale to any specific set of parameters. TCP has to work in all of those 4 scenarios. So TCP will achieve close to 100% in those 4 scenarios. We will see how in due time. Voilà, that's all we will see about the physical layer. It will come back when we talk about TCP and congestion control. Right now, I would like to first stabilize a few important things by what I call putting things together. So imagine here, I am transferring some data from a web server to a mobile. The web server is connected to Ethernet, and the mobile is connected to Wi-Fi. And assume that the two are directly connected by only one router, which is the simplest case. Then we can observe what happens at the mobile on the left, the router in the middle, and the web server on the right. The first thing we observe is that, so I'm showing the 5 layers of TCP IP on the left and on the right. In the middle and the router, I have only 3 layers, because a router is an intermediate system of the network layer, and one of the very fundamental design principles of TCP IP is this one. Routers do only the network layer, and below, of course, to be able to connect to the neighbors, but they don't do the transport layer or the application layer. This is a different way of saying again, in TCP IP, we do packet switching and not store and forward. Store and forward would mean the router would receive the entire file, therefore it will implement the transport layer and the application layer. But it does not. The router looks only at IP packets. That's the first observation to do here. Then we can look at the sequence of events and the terminology that goes with it. When the web server sends some data to the mobile, it uses some software that eventually, probably there are many layers of software, that at the end use the socket layer. The socket layer is the interface by which we use the transport layer. And one of the functions calls that we can use when we use a socket layer is send. Send through S2. S2 is the name of the socket. We'll talk about it again when we talk about the transport layer. And in lab 3, you will have to program that kind of things. A socket is a local descriptor, like a file, that says in which pipe I am writing to. Of course, S2 is associated to the other end, to the mobile, and to the mobile application on the other end. So the web server will do a call like send into that socket a block of information. The block is whatever the application is able to read. It can be 1 kilobyte, it can be 1 megabyte. Then this is handled by the transport layer, because the web and HTTP use TCP. And the first thing that the transport layer will do is break it into segments if it is too large, so that each segment fits inside an IP packet. So it will here create 5 segments. It will pass them to the network layer, and the network layer will add an IP header, which is shown in green here, that contains a number of fields, one important field being the destination address of Elaine's mobile. And then this is passed to the Ethernet card that will add a red header, which is the MAC header, that contains the MAC destination address of the router, because this is transmitted by Ethernet to the router. So this will propagate and reach the router. At the router, the MAC layer sees that a packet is arriving, receives it. Receiving it means get rid of the red MAC layer header and interpret what we have received as a sequence, as one or several IP packets. Of course, each packet will be received independently. We will not receive 3 at the same time. Now, the router, the job of a router is not to consume the packet, it's just to forward them. It's a switching center. So the router will analyze those IP packets by analyzing, in principle, only the green part of the header. The IP destination address probably is the only thing that's really interesting. It has some information that we will see in detail in a minute that allows it to know that it has to be sent over the Wi-Fi interface to reach Elaine's mobile. So it will send it now over the Wi-Fi interface by putting an orange MAC layer header. And of course, it's sent on a different interface than the one it was received on. Then it's transmitted over Wi-Fi. It reaches Elaine's mobile because it has the correct MAC address, hopefully. Then in Elaine's mobile, the MAC header is removed. Elaine's mobile receives IP packets, which are in principle the same packets with very little modification, are practically the same as the packets that were sent by at the source. It's like when you send a postcard, the postcard that you receive is practically the same as the postcard that was sent. The only difference being the stamp. So here's the same, the stamp is the TTL, time to live, that will be modified by the routers, but it's in principle exactly the same packet as was sent. So the network layer will now give it to the transport layer, and the job of the transport layer is to reconstruct the data that was sent. Reconstruction here means that if any of the packets is missing, it will ask for a retransmission. It will ask the transport layer of the web server to retransmit, but the application program will not see anything. And then the data is available in the transport layer buffer, and now it is not true that the transport layer would give exactly the same block as the application program wrote. The transport layer, in principle, does not give anything. It's the application layer that has to get the information from the transport layer. So the application program will do a read statement, which means receive, but here often we use the same terminology as with files. Will read from a socket that has a local name S1, and it will read some data. In fact, it will ask the socket, give me as much data as you have and as can fit in the buffer that my application program is using. Your application program may be a web browser that is rendering a page, including the photos, and the software that displays the photos, for example, does it by reading block by block. Now, the blocks that are read from TCP on the left are, of course, eventually the blocks that were sent by TCP on the right, but the blocking, the boundaries between the blocks, need not be the same. For example, it is perfectly doable to read on the left byte by byte. You could have a program that reads from the socket buffer 1 byte after the other. It's not very efficient if you want to display a photo that has millions of bytes, but it's doable. It would work. There would be no problem. In fact, there is no way for the TCP application on the left to know what block was sent on the right. When the file server or the web server sends 1 megabyte of information, this information is not available through the transport layer interface. So the transport layer interface has to find a way to know how much information was sent. It may be done in various ways. One way to do it is to read until there is nothing to read. So when you do a read statement and there is nothing to read, then the transport layer will block, or, depending on the options you have used, will return something saying there is nothing to read. Now, if there is nothing to read, it doesn't mean that's the end of the image, for example. It may simply mean that the image is still being transmitted. For example, there were losses that are being repaired, so it takes much more time. So it could happen that you have only a fraction of an image. Depending on how your software is done, you can see that somewhere a web display will sometimes show a partially received image. It's up to the application logic to decide when it has received everything. It can be done, for example, typically by having inside the application layer a set of meta information that gives when is the end of the image reached. So this information has to be encoded in the application layer. This is how things fit together here. A bit of terminology. The different packets that we see are called different names depending where they are. A packet that is created by TCP and sent to another TCP peer. So from the viewpoint of TCP, the web server is talking directly to a lane. The router is invisible. So the web server is sending one TCP packet to a lane, and this TCP packet is called a segment. The IP packets are called packets. The MAC layer packets are called frames. And all of those, in general, sometimes you will find this terminology, are called PDU. PDU stands for Protocol Data Unit. So this is a bit abstract terminology. That's not very useful, but you might see it in some documentation, so you have to be able to decode it. A layer N entities, for example, a transport layer. When two entities that are at the same layer send information to each other, the information that they send is called a protocol data unit. The protocol is the rules between two objects of the same layer. The objects that are passed to the upper layer are called the SDU, the service data unit. TCP can be used by an application program to deliver a stream of bytes. So the elementary, the atomic piece of information is a byte for TCP. The TCP SDU is a byte here. So the different PDUs are called packets most of the time, but sometimes frames, segments, etc. Datagrams also. More terminology in the labs, in the documents that you may read. We will see words like switches, routers, bridges, and many others. The terminology is changing all the time, and this is typical of computer science. People don't care about having a clean terminology, they just do it. They give whatever names is obvious to them, and then if they become very successful, you have to follow. At the origins of the internet, there was a cleaner terminology. A router means, in principle, a function. It means an intermediate system of the network layer. So a device in the middle that receives packets, analyzes their IP headers, and forwards them further. That is called a router. The very first routers were computers with multiple interfaces. Now, routers today can be your PC, that in the lab you will see how to configure it to forward packet. Then it's called, it becomes a router. It can be a big machine of Cisco, in which case people call it a router, or a smaller machine, in which case people call it a layer 3 switch. So the terminology is influenced by marketing, packaging, and the use of the device. But we have to navigate between all those things. It's impossible to understand what happens if you don't understand the functions that are implemented in a box. I will try as much as possible to use the words that have to do with functions. Router is a function name. At layer 2, an intermediate system of layer 2 that receives packets and forwards them, we'll see that that exists also, is called indifferently a bridge or a switch or a layer 2 switch. Switch has the connotation of a small device that is implemented in hardware. And all bridges today are small devices implemented in hardware. That's why they are called switches. But you can also have a bridging function implemented in software in your computer. In fact, the very first bridges were headless PCs that had multiple interfaces and were running a program for bridging. And I will terminate this section by what I call the onion view. The onion view is what we see when we do Wireshark, like you've started doing. With Wireshark, we can capture everything at the MAC layer and above. Not entirely all fields of the MAC layer, but practically all. We cannot capture what happens at the physical layer. So if we start at the MAC layer, we typically see a packet that contains a MAC header. The MAC header contains, in particular, the MAC destination address and source address. Inside the MAC header, there is a MAC, the useful part of it, of the MAC frame is called the MAC payload, and contains itself an IP packet. The IP packet itself has an IP header and an IP payload. The IP payload, if we're using TCP, will contain a TCP segment that has a TCP header and a TCP payload. So the useful information is only in the TCP payload in the best case here. So the bytes of an HTML file, for example. And this is what we can see when we use Wireshark, for example. And then we can start discovering some of the fields that are present. I mentioned the addresses. There are many fields, and that we will discover a bit later. So let's recap and see. So what is not shown in this diagram is the left part. You have to imagine what I showed 5 minutes ago. There is the router, there is a Wi-Fi local area network. On this Wi-Fi local area network, there is Elaine with her mobile. And the web server is sending a packet to Elaine. I close in 5 seconds. The correct answer is A, which you can see is also the majority answer. The MAC address is the address that is used to transfer the packet using Ethernet. Where is the packet going? It's going to the router. So the MAC address is the MAC address of the router. The IP address, remember, the IP packet shouldn't change along the way. That's the analogy of the postcard. So it should be the final IP address. It's the IP address of Elaine's mobile. So the correct answer is A. Let me skip this one. Good. So that is the end of this first overview chapter. In a few minutes, we'll now go more deeply into the IP layer. Are there any questions on this so far? Yes? Can you speak louder?
When we saw the communication among the two devices, we saw that the application layer of the receiver, which was the label, could receive the data with different blocks.
Yes.
We don't really get the fact about the fact that the data could be received in different blocks, things like that. I mean, in the whole picture.
So the question is to talk again about that picture.
Just the part when the reader reads the performance of the reader from the layer, data block could be designed.
So the question is on the reading side here, when the application reads data, what is that story of blocks and why is it not exactly the same block as on the sending side? The answer is that's the way TCP is done. So if you are a programmer and you use TCP, you have to imagine that the only thing you can do is to receive bytes, pull them out of a pool called the buffer in which they have arrived. That's all you can do. In other words, the TCP service interface, the service interface is the interface to the layer above. The TCP service interface is a byte stream service. Period. That's it. It's like when you read from a file. I mean, if you're writing a program that contains information that's in a file, then you need to read from the file, and then you need some way to know when it's the end of file, which is when you read a file. If you try to read until the end, you will get an end of file in the return of the read statement. Or you need to know how many bytes there are, or by analyzing the things you read, know if there is more to read. Right? With a difference compared to a file, which is that in principle the file is present on your disk entirely, whereas with TCP it's a stream. So the data is arriving, and you don't know when you read whether everything has arrived or not by TCP. Hopefully the application allows you to know when things have arrived, but by TCP alone you don't know. You see a sign of that when you display a web page, for example, depending on how it's written. It may be that the images will display later. So when a web page is typically an HTML file that contains embedded objects that require other files to be transferred. When you receive first the HTML file, if there is no and there are images, for example, if there is no indication of the size of the image, the web browser doesn't know how to display the image. But it has received already a text file, so it will display it. And then it will receive more, and as it receives more, it will know how to display. Yes? Question? You thought a connection could be closed and then you would know. Exactly. A connection can be closed, as we will see with TCP. TCP requires an association between the two ends, and when the server has finished transmitting, it will close the connection. And it will be visible to the other end, and then you know it's closed. So when it's closed, you know it's closed. But it may be closed because the interaction is finished. If it's not closed, you don't know whether it's not, you don't see it as not closed because the close message has not yet reached you, or whether there is more to come, whether there will be a new interaction, etc. Question?
If we had several routers along the way, between those routers, would there also be a MAC header on the connection?
If there would be several routers, then the routers have to communicate between each other. If they are connected by Ethernet cable or by Wi-Fi, yes, there will be MAC header. Now, routers can be connected by other mechanisms that are, for example, ADSL or optical fibers that have something like a MAC header, but that has a different name. It's called a PPP header. It's conceptually the same, but it may have a different flavor. But as a first approximation, the answer is yes. There is always a MAC header or a data link header between two routers.